Okay, so thank you all once more for being here tonight or today. We're going to start the second session, which is called Domain-Specific Computing. Davide Conficconi, who is postdoc and is going to be a young researcher in a couple of weeks from now. So he's going to be the session chair for this second research line in the NECSTLab. So without any further delay, we're going to have 5 talks that are going to be introduced by Davide.
Thank you, Marco, for the introduction, and welcome everybody. So I'm gonna briefly introduce you this research line at NECSTLab called Domain-Specific Computing. So briefly, who am I? As Marco said, I'm a postdoctoral researcher in the system architecture area, where I'm trying to focus on designing and co-design domain-specific architecture and systems. And moreover, I'm also doing several teaching activities in the field of computer architectures, reconfigurable system, and basic computer science. So, so far, if you have followed the whole flow, the traditional flow, you have understood that we have 3 research lines: IT for life science, domain-specific computing, and heterogeneous or high-performance computing. That will be the last research line. So I'm going to focus on DSC and briefly introduce you the context. So we are, you should be almost all familiar with this slide, which is basically saying that we are almost reaching the technological limitation of the current technology that we are using for general purpose computing architecture. And in this regard, there is a continuous tension between general purpose architecture and fixed function architecture that are striving to achieve the performance demand that is continuously growing and growing. So, however, since you cannot do almost everything or do only a few things, you can tailor your computation with the usage of domain-specific architecture, which are basically a way to tailor not to a single application, but to a broad domain of application. And in that regard, your domain-specific computation can have a lot of gains and benefits. The problem is that traditional domain-specific architectures, or DSAs, are mainly based on ASIC technology. This is a problem because not everybody can afford the time required to develop this kind of architecture, and that can somehow hinder your time to market or the capability to keep up with this algorithmic evolution. So that's why, for instance, here at NECSTLab, we are mainly tackling DSAs with the usage of reconfigurable system, with the so-called domain-specific reconfigurable architectures. We are trying to tailor our systems to the set of application, leveraging reconfigurable technologies. And this is, so what do we mean for domain-specific computing? There are several people currently in the research group, and we are tackling 2 main areas within DSC. On one hand, we are trying to build computer-aided design tools for building DSAs. And on the other hand, what we are trying to do is to focus on hardware-software framework, which means microarchitecture, programmability, for software programmable kind of architectures. And in this regard, example of the projects that you may find in this research line starts with SATL. So SATL is a prototyping, which is a library to build spatial templates for irregular application. I will not spoil many things because Francesco will give a talk about this specific research project. So please stay tuned if you're interested in knowing more. Then there is the hardware software framework for regular expression, where basically we are trying to see regular expression as a DSL, where we compile them into a set of binary instructions that feed and drive the software programmable core with different execution models that can be either depth first or breadth first. The other kind of project is the one that is focusing on bringing artificial intelligence from the dislocated cloud computing to embedded and edge devices, where in that sense, we can have gains with latency latency and throughput stability and gain more privacy. Specifically, in this research kind of project is focusing on decision tree machine learning algorithm. And you will see that there are two main approaches. One that leverage reconfigurable compute logic to accelerate this kind of decision tree algorithms, which is N3. And then there is the other approach, which is Yozue, which mainly leverage over memory decision tree acceleration. And Alessandro will give you more details afterwards about the Yozue approach. Another kind of project is Faber, where we are trying to build image registration pipelines that leverage accelerators, both FPGAs on GPUs, and you can deploy them based on a set of customization parameter, and basically Faber outputs for you the whole accelerated image registration pipeline. Always following this path, there is Hephaestus, which is basically expanding what Faber can do and on target not only 2D image registration, but also 3D image registration and achieve remarkable energy efficiency and speed up improvements. Last but not least, another kind of project is about design space exploration. Here, we are trying to target designers which are either willing to accelerate the manual development process, so more from an automation perspective, or would like to see how to find the Pareto dominance in their hardware architecture, which can be either through register transfer level or high-level synthesis kind of component. So this is a broad overview of DSC project. Today, we will have 5 different talks in the DSC area. The first one will be about automaton and regular expression from Filippo Carloni. Then Francesco Peverelli will dive into SATL, which are spatial architectures templates for irregular application accelerator. Alessandro will dive into Yozue for decision tree ensemble acceleration. And then we will have Paolo, which will give us a talk about unleashing the performance of Versal system for 3D image transformation, while Giuseppe will conclude this session pushing this image transformation beyond simple FPGA limits, targeting bilinear interpolation. So that's basically all from my side for the DSC area. If you're interested, those are the summary of the talk. I will not wait further, and I will leave the stage to the first speaker, which is Filippo Carloni.
Thank you, Davide, for the introduction. So, hi everyone, my name is Filippo Carloni, and I am a third-year PhD student here at the Polytechnic Milano. And today I will present to you one of the work in which I'm focusing on the last year, that is one automaton to rule them all, beyond multiple regular expression execution, on which I work together with Luisa Ciccolini, Davide Conficconi, and Marco Domenico Sant'Ambrogio. So before to start about talking the idea, I want to give you a brief introduction about what we mean about pattern matching in usual scenarios. Usually we have these patterns that, as we can imagine it, are called regular expression, and we want to find this pattern in a stream of data, a set of data, because we want to spot specific characteristics on this data. For instance, in network intrusion detection system based on signature, we want to analyze the network traffic entering in a private network with respect to a set of malware signatures, a set of rules that helps to stop and identify potential intrusion in this network. So the most common representation of this pattern, the user-friendly way, is about using regular expressions, while when we move to the recognizing step, we want to look at the finished state automaton. However, as in the case of Snort or Suricata, that are network intrusion detection system, or proteomics, usually have a lot of regular expressions, so patterns that we want to identify with respect to a single data. And this is the problem, because usually this implies a lot of states, a lot of memory usage, and for sure, a high latency that is not always achievable, for instance, in the case of filtering packets. So from this observation comes the idea on, we do better about in looking at a single dataset? And this is the idea about, there are some similarities between these patterns in a benchmark, in a dataset. So we started trying to quantify, at least in a tentative way, this type of similarities, and with the Indel similarity index. And we can see that there is a quite high similarity in these most common benchmarks, for instance, in Protomata or in TCP, that are, the last one is intrusion detection, which the first one is about proteomics. And thus comes the idea. We want to propose a new model to try to merge together a set of regular expression in trying to optimize both the memory efficiency and the latency. Then we propose a way to compile the regular expression into this new type of representation. And finally, we want to evaluate the impact of the new model in the execution perspective. Coming back to the idea in how to identify, in how to merge this type of set of regular expression into a single new automata, I start these two representative regular expression that are general exemplification, in which we have the starting regular expression and a common sub-patterns, some common sub-patterns that are shared from the regular expression 1 and the regular expression 2. Then we want to put together these two patterns and, of course, the merged part together without repeating this type of sub-patterns. However, as we can see from the graph, from this representation, we then created new lines with respect, new edges, so new connection between states with respect to the starting regular expression. For instance, we have the path from 1 to 2 to state 2 to 3 and then to 4, or we can go from 2 to 4. However, it's not intended to go from state 2 to state 4 in the initial regular expression 1. And this is the problem, because in this way, we are allowing new false positive, new representation, new accepted language that are not accepted from the native regular expression taken in input. And thus come our idea about developing an activation function. Activation function has the concept that keep tracks of which regular expression are merging during the traversal of the automaton, and if that type of regular expression can go further with respect to an edge with respect to another. So basically, we are keeping which regular expression are matching and which regular expression can go further in the traversal of the automaton if they are allowed. In this way, we remove the problem of patterns that cannot be taken from a regular expression with respect to another. So coming back to what composes the model, we have as in the classical finite state automaton, we have the states, the alphabet, which represent which characters we can analyze. Then we have the initial states, in this case are the initial state of each regular expression that we want to recognize. Then we have the final states, representing when a match occurs, when we reach that final states. We have, as a classical FSA until now, also the state transition, so how an automaton can move further from a state to another. But with respect to the standard FSA model, we have with the MFSA, the FSA activation function, which, as anticipated, keep tracks of which regular expression are matching and which regular expression can go further in the matching of the single traversing in the automaton. And of course, the set of identifier for the regular expression that we are considering. This represents the first contribution, that is a novel formalization of the class with respect to the standard FSA representation to support this concept of merging regular expression together in a single automaton. And then we have how to compile a representation that is a regular expression into an MFSA. First of all, we have the syntax and lexical analysis. So basically, we take the regular expression as input, we check if they are well formed, and then we move to the FSA generation. Until these steps, we are looking at the regular expression singularly. Then we move to the merging operation that basically takes a set of regular expression and puts together this regular expression in a single novel MFSA automaton representation. The set, how many regular expression we want to match together is the merging factor that we will see in the experiment can be increased with respect to how many regular expression we want to put together. This represents the multi-level compilation framework that is the second contribution of this work. But then we have to analyze on how to match the data with respect to this new model. So let's start with an example. We have two simple regular expressions. This first one that matches basically C, B, A, and B characters. And then we have the second regular expression and the representative automaton that matches A followed by B or C. And these are the two equivalent representations in automaton language. Moving now to the MFSA representation, we can consider first that we have reduced also in this exemplification the number of states and transition. And however, now we have to consider multiple regular expressions when traversing this automaton. For instance, starting from the string to match in input that is S, we have first of all A that activates the second regular expression in the state 4. Then we have the C that basically concludes with a match for the second regular expression, but also activate the first one regular expression in the state 1. Then we have a B that moves forward in the matching of the regular expression 1. Then we have another A that in this case activate both the transition for state 4 to 5 for the regular expression 1, because in the path to match that started from state 1, but also activate against what is the regular expression 2. So in this case, we have an activation set that is composed from regular expression 1 and 2. Finally, we have a B that represents a match for both the languages. And so we have a double match also in this case. So finally, we have 3 matches, 1 from regular expression 1 and 2 from regular expression 2. That is achieved only with a single pass in this automaton. And this is the point about using MFSA. We then implemented this type of idea in Infant, that is one of the most famous and state-of-the-art algorithm about non-deterministic finished state automaton execution on parallel architecture. And then we checked that it guarantees the same accuracy. And of course, we evaluated how the latency changed while employing or not the MFSA model. So coming to the experimental evaluation, first of all, we evaluated how much is the impact about introducing this merging step compilation, which is the compression ratio that can we achieve in using MFSA with respect to keeping the standard FSA representation, so having 100 of regular expression with respect to the compression version. Then we have evaluated the infant execution on a desktop CPU to keep track of which is the latency improvement or decreasing with respect to the standard execution. So starting from the compilation time overhead, we can see that the compilation time is quite low. However, in the current implementation of the merging procedure, we have a sub-exponential compilation time. If it's possible to pay this small overhead in compilation, we can see that starting from the state compression, while increasing the merging factor, we can achieve a top geometric mean average that is about 70% in state compression with respect to not having compressed the automaton or the regular expression equivalent representation. And this is, first of all, what it does imply a reduction in memory utilization, because we are basically representing the 70% less of the state with respect to the standard representation of one automaton. Coming now to how much is the latency with respect to the classical implementation. First of all, we evaluated this model in a single thread configuration. So basically, we have one single thread while we trying to increment how many regular expressions we are merging in the new model. So the first one, the merging factor equals to 1, meaning no merging factor. Basically, we are looking at single automaton. Then we have to merging factor equals to all. That means basically, in this case in this evaluation, 3 under the regular expression merged together. And we can see that usually we reach a sort of plateau in how much we can reduce the execution times. And usually it is the merging factor equals to all for at most all benchmark. Exceptionally, .*9 and Protomata have a better improvement while keeping a lower merging factor. However, looking also in this case at the top configuration, we have a geometric mean improvement in the single time evaluation that is about 5.3 per with respect to the single thread evaluation with the native FSA evaluation. So no merging factor with respect to our proposal. Now moving to more real scenarios in which we have also a processor which can exploit an increasing number of threads. In this case, it's a desktop processor with 4 core and 8 threads. You can see that this naive approach, so the standard approach in which we have a lot of FSA and a lot of thread, we reach a sort of plateau in the number of achieving in the lowering the execution time, so the latency. And of course, we stay usually on the number of threads that is from 4 to 8 because it's the core limit of the architecture. However, if we propose the execution of MFSA, you can see that we can lower this latency in 2 types of configuration. The first one is about keeping the same throughput. We can see that if you want only to keep the same throughput, we can reduce, in average, we can halve the number of threads that we want to use. And this evaluation is on the blue circles. Then if we have no limits in about how many threads we want to use, and we want to achieve the maximum number of MFSA and threads, so we want to have the lowest latency in absolute values, we can see that in red, you can lower with a geomean speed up in top configuration that is about 4 per with respect to not having used the MFSA model and in the multi-thread evaluation. So basically, we have an improvement in 2 different types of experiment. One is we want to achieve the same throughput, but we want to use lower thread, and this is possible using MFSA. And we want also to achieve a lower execution time using how much as thread as possible, and we can do this using MFSA. Looking at the future, we are working on improving the MFSA algorithm. We want to lower the plateau that we can reach in executing of MFSA in infant. We want for sure reduce the impact of the merging procedure in the compilation time. And we are looking at trying to possibly support advanced feature in regular expressions that are not classically supported from standard FSA model. This concludes my presentation. If you are interested, feel free to have a look at the code or the preprint paper that is available on GitHub. And thank you for the attention.
I have a question for you. So please elaborate a bit more on why on some benchmarks we have seen that the merging factor of the whole rule set is not the optimal one.
You are referring to this picture, right?
Yes.
Okay. So we are a bit strange when we see that, of course, the merging factor equal to all is not the best case, but as I anticipated, when we traverse the automaton, we have to keep track of how many regular expressions we are merging. And we also see that in this type of benchmark, so .*9 and Protomata, have the problem that they are already a large number of active transition in the single FSA evaluation. So adding in this case an overhead about how many regular expression can keep active during the traversal of the automaton has reduced the maximum number of regular expression that we can match together, because of course, if we have a lot of partial match, we have a lot of regular expression that are active in traversing the automaton. And this is a problem because we have to investigate and check whatever this regular expression can be keep active during the continuous of the traversal of the automaton.
Okay. Thank you, Filippo, for the talk. So I will stop sharing and I will pass the word for the next speaker who is online with us, which is Francesco Peverelli.
Thank you, Davide. I'm sharing my screen.
Yes. Okay.
Can you see the slides?
Perfect.
All right. So yeah, thank you, David, for the introduction. So my name is Francesco Pavarelli, and I'm a third-year PhD student at NECSTLab. And today I want to talk to you about my research work on special templates for acceleration of irregular applications. So first of all, I want to briefly introduce the context. It has already been stated in the introduction, but basically I'm focusing on the HPC scenario where we have a very heterogeneous set of applications that all have something in common, which is they have an ever-increasing demand for more performance. But we know from technological limitations that classical polynomial architectures are not sufficient. They cannot satisfy the increasing performance requirements. And therefore, we have a push for the investigation of novel architectural models. So the question is, how can we go about this? And from this, we have the idea of investigating template-based spatial architecture. So let me break this down for you. So spatial architecture generally intend to be architecture where we have a spatial distribution of processing element and memory elements. And these elements are interconnected in an application-dependent topology, which is devised to optimize the performance of the architecture. And the reason why we are interested in templates is because we want to have an abstraction that allows us to more easily combine, experiment, and prototype architecture to figure out which one fit our particular use case. So existing work has been developed in the automatic generation of spatial architectures, but generally speaking, these works focus more on architecture that target computation which are very regular. And this is because leveraging this regularity and the simplifying assumption, it is, let's say, much easier to identify which topologies and which architecture would be optimal for a particular application. However, this is limiting in the applicability of this approach, and therefore SAT wants to be an expandable collection of building blocks for the design of templates for spatial accelerators, but that specifically focuses on irregular applications. And in doing so, we want to provide three main key functionality. So the first one, of course, is specializations, which refers to the fact that we want to be able to instantiate a component which is as specific as possible in order to extract the maximum performance from our architecture. But also we want modularity, which is intended to facilitate hardware reuse and allows us to create designs that are parametric by construction. And together with modularity, we also would like to have automation. In this context, what we mean is the automation of integration between components. So we have different specialized components that can be then easily integrated in different ways. So experimenting, for example, with different topologies in a very lightweight version. So let's have a look at what the design flow with SAT looks like generally. So the idea that we have some computational kernels that we are interested in accelerating, and therefore we analyze these kernels and we focus on two particular aspects. So the first one is data movement patterns, so how our workload moves data. And the second one is what operations are required to perform our workload. So these two aspects directly map to the idea of the optimal interconnection topology for our template and the type of processing element that we want. So then we would use the template library to compose different components available to create a template prototype. And we can iterate this process until we, of course, reach a configuration that is performant as much as we would like. So focusing on the types of components that we have in SATL, so we can broadly have three distinct categories. So the first one is processing element, which are elements that are devised to, again, carry out the actual computation on data for our application. Then we have memory elements, which are generic description of elements that can hold data, so different types of memory. And then we have the subcomponents of the processing elements, which generally are of two types. So we have address generators, which are generally components that are tasked with handling how our processing element interacts with memory. And then we have data flow engines, which are components that are designed to handle how our PA will carry out the computation. So beyond the library components, SAT offers an overall prototyping and acceleration flow. So in this flow, since we've said we're focusing on irregular application with a major focus on data, we envision the fact that besides the target kernel, we also have a target input that we, let's say, use to carry out the kernel analysis. And once we have carried out this joint analysis, co-design between application input and template, which we can iterate through a chisel-based simulation, then we can move to the prototyping phase. In this phase, we have two distinct flows, a chipyard flow, or let's say a prototyping flow, which uses the template integrated as an SoC with a RISC-V processor, and the template that acts as a ROC-based coprocessor. Then we can use Vivado to basically prototype this whole system on an FPGA. Another thing we can do with such is instead opt for a more acceleration-based flow, which means that we're not prototyping, we are trying to create an FPGA with accelerator from our design. And in this case, we can use the Zinc-Autoscape Plus MPSOC to have a hard CPU that acts as the host for our processor, and the template is then connected and implemented in the FPGA programmable logic. So I will present 3 case studies of different applications we have accelerated with SATL. So the first one is SPMB. So SPMB is a ubiquitous kernel in HPC that consists of the multiplication of a sparse matrix with a dense vector. So this kernel can be parallelized in the sense that we can compute different rows of the matrix in parallel, and we can defer the accumulation to local work within the processing element. An important and challenging aspect of this kernel is that we have an indirect access to the X vector. Therefore, we would like to optimize the shared memory access to this data. So based on these assumptions, we can envision a parallelization that looks something like this. So we have different PEs that compute different rows of the matrix, and we provide shared access to the X vector. So let's look a little bit more in detail at how this template is created with SATL. So we have an SPMB template, which implements what we call component traits. So these traits define which subcomponents are present in the template. So in this case, we have an end-to-end memory interface to interconnect memory with the PEs. We have a data flow-based processing element that will compute the multiply accumulation, and we have DRAM-like memory element that will hold our data for both X and the sparse matrix. So in order to achieve the automation aspect, the SPMB template also implements interconnection traits. These interconnection traits, different from component traits, do not enforce the presence of modules, but allow the use of interconnection methods on these modules. So this interconnection method allows us to easily integrate the different components of our template. And lastly, the specialization aspect is achieved by, let's say, iteratively extending the generic classes to then achieve the specialized components that we need. In the example of SPMB, we have an SPMB-based flow engine, which is a multiple accumulator, and we have a SPMB-specific address generator, which reads data according to the data access pattern of the SPMB application. So this is a brief overview of all these components and how they're implemented. So as you can see on the left, we have the components for the SPMB processing element. We have the address generator, which starts with efficiently reading data from memory. Then we have the flow engine, which is the one carrying out the computation, and the SPMB PE is the data flow PE that integrates these two components. On the right, we have the remaining component, which are the memory interface. In this case, we have a many-to-many memory interface, which connects all the memory banks with all the PEs to provide parallel access to the X vector. And then we have a controller. In this case, we showcase a ROC-based controller that is used together with the PEs and memory elements to orchestrate the computation. So as we said, here we are going through the chipper-based prototyping flow. So this is implemented as a ROC accelerator in the chipper SoC framework. And what we did was experiments with different, let's say, sparsity pattern for the input and different application domains of origin for the input matrices, and several iteration of the architectural templates with different architectural features, and we evaluated their impact on the performance of the overall architecture. So I will not describe them all. I'll just briefly give you an example. So When we carry out the SPMV computation, we can notice that although the X vector needs to have access to all the memory banks at once, or rather the template can read from any place in the X vector, the access pattern for the sparse matrix is much more regular, and it can be, let's say, tied to the single processing elements. So we go from a single memory interface that connects all the memories to all the PEs to a memory interface, first memory interface that connects only the X vector buffers to memory with all the PEs, and that connects each PE with their local data for the sparse matrix. And then we evaluate what is the impact of this change on the different datasets. So we can see G1 through G7 are groups of matrices that have been grouped by application domain. And we can see that depending on the input data, for some of these matrices, adding vector buffer has a significant positive impact on throughput, whereas for some other workloads, it's really not that relevant. This is one example of the kind of investigation we can carry out prototyping with SAT. Subsequently, we move to the second case study, which is the acceleration of the symmetric considered kernel. So this kernel is similar in terms of the data access pattern to SPMV, but has one key difference. So since we are updating the X vector at each outer loop iteration, we can no longer simply parallelize across the rows. So we need to figure out a more sophisticated way to parallelize this kernel. This is why we developed many two things. So one is a custom CSR format that allows leveraging coloring strategies to allow us to process the data in parallel. And secondly, we have specialized adaptable generator to allow for fast synchronization between the execution of different colors. So this led us to achieving very good parallel scaling efficiency in this architecture. So in this graph, you can see that we have taken several input matrices, and we are comparing the parallel efficiency of our DSAs with a CPU processor. So we have on the left a Ryzen Dexter processor, and on the right an Intel Xeon Gold HPC processor. And we can see that the software implementation, which is a coloring-based parallel implementation of HPCG, struggles to have good parallel efficiency if we increase the number of threads. Conversely, our architecture with our fast synchronization strategy is able to have very good parallel scaling by increasing the number of PEs. The first and last case study is an architecture that is designed to carry out decision tree inference. So we implement with SATL memory-centric accelerator for decision tree inference on embedded platforms. So this architecture is taken from a state-of-the-art Vitis HLS design, which operates largely around with the same assumption and as the same architectural structure. But we've taken this design and we implemented with the SATL framework. So Alessandro in the next talk will give you more detail on this original HLS design and the application. Here I will mainly focus on how we use the templates-based methodology to design this accelerator and what we gained. So in the case of this template, we need a point-to-point interface between the processing elements and the memory elements. We need a one-to-one interface between processing elements, which is the directed ROCC that connects each PE, which we didn't have previously. And since the decision tree computation is very, let's say, regular, we can employ a fixed latency processing element as opposed to a data flow-based PE that we had in the previous example. So in this case, we're not following the prototyping flow, but instead we are going with the FPGA acceleration flow. This means that we take the template and we implement it on the Zen scale plus MPSoC. And then everything is synthesized with Vado, and we end up with a full-fledged FPGA accelerator. So we can see that as opposed to the HLS implementation, the SATL-based implementation can support up to 4.2 times more trees, which allows us to be able to evaluate larger datasets and decrease the critical resource use, which is lookup tables in this case, by more than 2 times for the same configuration. On the same token, SATL also increases the throughput we can achieve. So we go from, so we increase by almost 3.6x throughput with respect to the baseline Vitis HLS design. So we can see from this example that SATA is not only useful in terms of prototyping and experimental in new architecture, but also to have a more optimized and efficient versions of existing architecture, which are, for example, implemented for high-level synthesis, which introduces a bigger overhead both in resources and a decrease in performance. So this was all from my side. Thank you for the attention. If you have any question, feel free to ask.
Thank you, Francesco. I have a question for you. So, do you plan to support different FPGA flows with other than the Zinc MPSoC one?
Yes. So if we go back to the current flow, you can see that for the acceleration on FPGA, we only have the Zinc Cascade Plus, and this is because this matches the chipyard SoC, let's say, paradigm, where we have a template which is a tightly coupled accelerator with an interface directly with the processor. However, this is not always optimal for all cases, and sometimes we would like to have a more decoupled accelerator, for example, memory map accelerator. And we plan to extend support for this. More in particular, we would like to be able to create an AXI master-based accelerators that uses the flow that can be, for example, employed by Alveo boards to have more high-performance oriented FPGA accelerators.
Thank you, Francesco, for the presentation.
Thank you.
I will start sharing. Because now I give the word to wrong presentation. Okay. Now I'll give the word to Alessandro.
Thank you, Davide, for the introduction. Hello, everyone. I'm Alessandro Verosimile, and today I will present you Yosewe, trimming random forest training towards resource constraint inference on FPGA. First of all, let's introduce myself. I'm a first-year PhD student in information technology here at Politecnico di Milano, and during my PhD, I'm working on the optimization of machine learning algorithms for systems with scarce resources. So, the main focus of this work is artificial intelligence of things, the combination between Internet of Things with all its interconnected devices and artificial intelligence with all its powerful algorithms. Artificial intelligence of things is becoming more and more important in nowadays technology, finding application in multiple fields such as video surveillance and automotive, thanks to the possibility of running also on small IoT devices the inference of powerful machine learning algorithms. And this is giving the possibility to such IoT devices to perform their tasks better or to perform new tasks as were unaffordable before. The weakness of artificial intelligence of things is that such IoT devices need to rely on cloud infrastructure to run the inference of such big machine learning model. And so they need to rely on an internet connection. This approach is not suitable if such IoT devices perform critical tasks due to the instability of latency and throughput and due to the privacy and security risks that are connected to the unstable and uncontrollable nature of the internet. Therefore, the ideal solution would be to keep all the computation on the device, to perform the inference directly on the Internet of Things device. The problem is that such device is resource constrained and has a low computational power. Therefore, it is of critical importance to design and optimize a domain-specific architecture that can run significantly large machine learning model on embedded systems with reasonable performance. The first important question that we have to ask ourselves is which is the most suitable model in this context? And the main choice is between artificial neural networks and decision tree-based ensemble models. And in our case, we choose this second option because not only because such Ariette et al. Says in their survey about explainable artificial intelligence, tree ensembles are arguably among the most accurate ML machine learning model in use nowadays, but also for their high level of parallelizability. In fact, during the inference of random forests, a particular category of decision tree-based ensemble model, each tree is inferred and it assigns a class to each sample. And then a majority voting operation is performed to obtain the final score. And this approach allows for two types of parallelization: horizontal, because each tree can be inferred independently from the others, and vertical, in the sense that each level of the tree needs only the information of the previous one to perform computation. And so this allows for hardware pipelining. The second important question that we have to ask ourselves is which category of architecture is the most suitable for this context. And the choice is between general purpose architectures and domain-specific architectures, such as FPGAs and ASICs. And we will choose this second one because we would like to optimize a domain-specific architecture for the inference of random forests on embedded system. And we would like to optimize it to be resource efficient, to be adaptable to a resource-constrained context. So we can set the goal of Yosewe: build a domain-specific architecture for the inference of random forests on embedded systems, and therefore in a resource-constrained scenario. In this context, there are two main design methodologies to build a domain-specific architecture: the logic-centric one and the memory-centric one. In the logic-centric approach, the model is directly hard-coded as logic into the hardware, allowing for a high throughput, but this approach is also highly resource-intensive. So it is not the most suitable one for a resource-constrained scenario. The second one is the memory-centric, in which the model is encoded as instructions that are then stored in memory. Then a set of processing elements will fetch instructions from these memories and perform computations over a stream of samples. In the state of the art, there is already a work that uses a memory-centric approach to perform the inference of random forests, and this work is RFRASA. In their work, they store the instructions of each level of each tree in a different memory, allowing in this way for hardware pipelining, because each processing element will only need the information of the previous one to understand which instruction needs to be fetched. The problem of such approach is that there is a huge waste of resources caused by the fact that for each new tree of the ensemble, a new set of memories and processing elements needs to be instantiated. So Yosewe will build over this architecture to improve this inefficiency. So starting from the architecture proposed by RFRASA, the main optimization done by Yosewe is to fit more trees in the same set of memories. A new set of memories and processing elements will be instantiated only when the first one cannot accommodate any other tree. In order to allow all the samples to execute all the trees into the same set of memories, a loop needs to be added. So the pattern of instructions in memory after this optimization is this one. And we can notice an exponential pattern. The memories that are related to the deepest level of the trees will be almost full with a small number of trees. And with the same number of trees, the memories that are related to the shallowest level of the trees will be almost empty. And so also in this case, also after this optimization, we still have a significant waste of resources. We would like to use this space in a smart way. And the most intuitive thing that we can do is to add other trees. But we cannot add other trees at the maximum depth. So we will add trees at maximum depth -1, -2, and so on, building what we can call multi-depth random forest. This approach is completely sound from an hardware perspective. We are adding new trees without instantiating new memories, so without any additional memory overhead. But we have to ask ourselves if this approach is suitable also from a machine learning point of view. So if such multi-depth random forest will have comparable performance with respect to a full depth random forest with the same number of trees, but all of them at the maximum depth. And the answer to these questions is probably not, because our multi-depth random forest is a smaller model that has less capabilities to capture the pattern of the dataset. So what we expect is a significant drop in the performance of the model. For this reason, considering that we would like to keep the shape of such model, we need to optimize its model performance. And we will do it through this pipeline. Starting from the datasets, we will train several random forests at different depths. Then such random forests will generate their predictions over a second portion of the dataset. And these predictions will be weighted through a small one-layer neural network. Then the weights of this neural network will be extracted and used in hardware for the inference. The validation of such approach has been tested over 5 different datasets taken from the UCI machine learning repository. What we are looking at in a single box of this heat map is the delta of accuracy between our multi-depth random forest and the full depth random forest with the same number of trees, all of them at the maximum depth. And what we can notice is that on the left, we have a significant drop in the performance of the model in all the combinations of number of trees and maximum depth. So we can forget about it, and we can focus on the situation where we weigh the contribution of the single depths. And in this case, we can notice that on average, we have a negligible drop in the performance of the model. But moreover, we can notice that the best configurations are the ones that are widely used from a machine learning engineer. Instead, the worst configurations are the ones that are strongly discouraged in the state of the art, because they combine a small number of trees with a high depth, and this often leads to overfitting. Last but not least, the Yosewe architecture has been optimized through the spatial template architecture previously described by Francesco. SATL provides composable and standardized components into a chisel library, and Yosewe uses such components to have a low-level control over the computational and memory elements of its architecture, allowing to improve its throughput and to reduce the utilization of resources. So let's move to the experimental evaluation of our architecture. Starting from an example of the proposed Yosewe architecture, we added a timer to measure the throughput and the latency, and a DMA to simulate the stream of samples coming from an IoT device. The experiments have been run over an AVNet Ultra 96 version 2 board, which mounts a Zinc UltraScale Plus SMP system on chip, with hardware parameters that are coherent with the Internet of Things context. So, first of all, let's present the results related to the throughput of the architecture. We are comparing to the RF-RISA version on embedded systems, so re-implemented on the Ultra 96 version 2 board. And we can notice that due to the conflicts introduced due to the loop of the Yosewe architecture, the standard version of Yosewe has a drop in the throughput in all the configurations. But this drop in the throughput is gained again thanks to the optimization done with SATL, leading to a throughput that on average is the same of the RF-RISA implementation on embedded systems. But the most important result relates with the synthesizable configuration. In fact, if RF-RISA can run not more than 4 trees with a maximum depth of 5 on embedded systems, Yosewe can run more than a number of trees that is 2 orders of magnitude greater with respect to the state of the art. And thanks to the optimization now with the spatial template architecture, there is an additional 4.2 times increment in the number of supported trees. So, in conclusion, we developed a domain-specific architecture for the inference of random forest and a new decision tree-based machine learning model, specifically designed to have an efficient inference on such architecture. The union of these two contributions allows Yosewe to run a number of trees that is 2 orders of magnitude more with respect to the state of the art. Moreover, thanks to the optimization done with the spatial template architecture, we gain an additional 4.2 in the number of supported trees and a 3.5 increment in the throughput with respect to the standard version of the architecture. So, this is the end of my talk about Yosewe. If you are interested in this topic, in the inference of decision tree-based ensemble model on embedded systems, on to the optimization of any other machine learning model in a resource-constrained scenario, you can just send me an email and we can talk about any possible collaboration. So I thank you all for your attention, and for any question, I will be more than happy to answer.
There is some role for your talk. I have a question for you, which is the bottom of the service that is open right now failure of this synthesis in some configuration that you presented with yourself.
Yeah, the bottleneck resources is the number of used lookup tables. So also, if this architecture is memory centric, reducing the number of employed memories, we have considering that we have a one-to-one map on the processing elements to the memories. Reducing the number of memories reduces also the number of processing elements that are the main element that consumes lookup tables. So the bottleneck resource in this specific case are the lookup tables, and we are reducing its utilization, reducing the number of used processing elements into the architecture thanks to the optimization done by yourself.
Thank you, Alessandro, for your presentation. So we now move ahead with the following talk, which is from Paolo. So, Paolo, I leave the stage to you.
Thank you, Davide. Hello, everyone. I'm Paolo Calfano, and today I will present you Unleashing Versal Systems for 3D Image Transformation. But first, a few words about myself. I'm a computer science and engineering student here at Politecnico di Milano, and my studies and research interests mostly cover computer architectures, FPGA, and computer graphics. In this project, I've developed an accelerator to accelerate 3D rigid image transformation, which basically consists in translating and rotating a 3D volume while preserving lines, parallelism, and angles. Among the many applications for transformation, registration stands out. 3D image registration is an image processing technique which consists in indeed translating and rotating a 3D volume to align it as best as possible to another reference one. It is applied in many fields, but here I focused on the medical field, in which it is used for robotic surgery, for example, and medical image analysis. And in this field, in the medical field, it's crucial to do it with high accuracy, high energy efficiency, and with low execution time. To achieve a registration algorithm performs iteratively these three steps. First, it determines the parameters of the transformation using some research algorithm. Then it actually performs the transformation, and finally it computes a similarity metric, which is useful to assess the quality of the alignment. If, as the alignment is not good enough, these three steps are repeated over and over until the two volumes are aligned correctly. Now, this process has a problem. The transformation and similarity metric computation steps are highly computationally intensive. Indeed, literature has proven that they are the bottleneck of registration. Indeed, the aim is to develop a solution, an accelerator, that can achieve low execution time and high energy efficiency. But of course, this is also the aim of many other works in the state of the art. Regarding similarity metric, FPGAs have been proven to be the best solution to accelerate it, as they can achieve high speed and high energy efficiency. But for transformation, things are different. They are best accelerated with GPUs. Indeed, some software libraries like Cornea, MATLAB, and OpenCV support also GPU acceleration, but GPUs are too power hungry. So there are also FPGA-based solutions, which instead have a good energy efficiency, but they have unsatisfactory performance for the medical domain. So we have that the transformation is that part of the computation that still needs to be tackled, as it suffers from the trade-off between performance and energy efficiency. For this reason, we would like to have a solution that merges the benefits of SIMD architectures like GPUs, that is high performance, and also the benefits of FPGAs, that is high energy efficiency. But if we wanted to do so with one single device, one single board, there was no way to do it before 2019, as there was no single board which mounted both a SIMD and an FPGA directly interconnected. Then Xilinx in 2019, which now is AMD, released the Versal, which is an adaptive compute acceleration platform that has two general purpose processors. It has the FPGA and the AI engines, which are an array of 400 belief processors with vector unit, which makes them a SIMD architecture. And it is indeed by exploiting this heterogeneity, which have developed a framework that accelerates 3D rigid image transformation by devising a methodology that integrates the FPGA and AI engines to exploit the heterogeneity. This framework is also pluggable into an existing state-of-the-art similarity metric FPGA-based accelerator, thus proving itself in the task target of image registration. One of the main challenges and main contribution of this project was to map the computation on the hardware substrate. That is, use the FPGA and AI engines to do what they do best. Before seeing the mapping, let's first analyze the structure of the computation. We have two macro stages. First, a geometric transformation step in which, given some parameters and a set of coordinates, the transformation is applied. And then in the fetching stage, the transformed coordinates are used to locate in memory a pixel and then read it. So this is how the computation has been mapped. We have the compute-intensive part, the geometric transformation, which is done on the AI engine. And then we have the memory-intensive part, which is the fetching, which is done by a fetcher kernel implemented with an FPGA. Now let's focus on the fetcher kernel, which is the component with the most constraints and limitations. Indeed, a big constraint we have in this project, which is that the output must be generated in a deterministic and sequential order. But as transformation is a procedure that moves pixels around, requiring that it generates a sequential output means having to read the volume from memory following a random pattern. But random accesses in memory limit performances. This is because if we want to read 1 pixel at a time, we have to perform one read request for each pixel. And we have a latency between a read request and the time when the data actually arrives. If instead we perform sequential reads, we can group together multiple pixels and perform one single request for all of them. This is called burst, and it's implemented by the AXI protocol. Moreover, if we perform sequential reads, we can also further group pixels together and read them in parallel, thus widening the bit width of the reads, further decreasing the latency and increasing the reading throughput. But to do so, we have to use a specific data layout, which allows to read sequentially. This is a depth major layout, in which pixels along the depth dimension are stored sequentially in memory. This layout allows to exploit the burst and by bit width widening to increase as much as possible the reading throughput. Now we have seen the fetcher. Let's now see the geometric transformation, which is implemented in the AI engine. Programming the AI engines means dealing with statically scheduled compiled code, which actually requires the programmer to be extra careful in ordering the operations of the algorithm, so that because the order highly impacts the performance of the algorithm. Moreover, AI engines are memory constrained, so the programmer must be, again, extra careful in how we stores data in the AI engine local memory, so not to saturate it. And also, the program size, or let's say the memory which is dedicated to a program, is very limited. So the operations chosen for the algorithm must be chosen in such a way that the program size fits in memory. But the AI engine has a vector unit, which is that component which allows it to execute operations on multiple data at once. Exploiting the vector unit, I've developed the geometric transformation algorithm, in which first we select a chunk of 32 coordinates. 32 is the maximum amount of data on which the AI engine can perform operations. Then on these 32 coordinates, I perform the transformation using floating point operations. Then from the transformed coordinates, I derive the indexes. An index is what basically says the fetcher where to locate the pixel in memory. Finally, as some index may refer to pixels outside of the volume boundary, we have to filter out those indexes. And this is done in the last step before passing these indexes in output. Now we have seen also the geometric transformation, so the whole design has been covered. Let's see how it performs. I've used a dataset which is pretty standard in the medical domain, and I've measured the execution time and energy efficiency. The introduction of the new data layout brings a speedup of 21.6 times thanks to the AXI burst. But we have to consider that only changing the data layout, introducing it without implementing actually the burst, it already brings a speedup of 10.5 times. This is thanks to design choices that needs to be made to support the data layout, which already bring a noticeable speed up. Moreover, the design can be scaled, that is, the number of bytes which are read in parallel can be increased. Indeed, the best performing configuration is the one where 128 bytes are read all at once. And it achieves a performance of execution time of 7 milliseconds with a speed up with respect to the version, the single byte version of 46.1 times. We have to consider that the best performing configuration is not suitable for the state-of-the-art FPGA framework for the similarity metric. Indeed, the 16-byte version is the one that can be used for it, which has still a good performance of 22 milliseconds for the transformation. Comparing the best performing configuration for the transformation against the state-of-the-art framework Cornea on high-end hardware, that is the NVIDIA A100 and A5000, this framework achieves a speed up of 127 times with an energy efficiency improvement of 322. Moreover, considering the target task of image registration, the configuration which is a bit worse performing, the 16-byte one, again against Cornea on the same GPU, it achieves a speed up of 42.2 and an energy efficiency improvement of 116.9. This proves that this design actually does merge the benefits of FPGAs and AI engines by beating state-of-the-art in both transformation alone and an image registration step, both on high-end GPUs and FPGA. In the future, there are many things, many ways in which the design can be expanded, for example, by validating it with, within an entire registration procedure, but also we can extend it to apply it on other domains. For example, if you work in automotive or you do computer vision or robotics, transformation is probably a very important task for you. So accelerated using a framework like this may be very helpful. Or again, in automotive or machine learning or robotics, or even if you work in embedded systems, having solutions which have both high energy efficiency and high good performances is crucial. So in general, heterogeneous systems may be what you are looking for. So I'm open to collaboration. So if you want, drop me an email and I'm happy to collaborate. Thank you.
I have a question for you, which is about the execution time that you showed us that does not decrease when moving from 128 bytes to 156 bytes of for writing.
Okay, so you're
explain a little bit more why this.
I guess you're talking about this this graph.
Exactly.
So we have that while scaling the bit width, we have that the reading speed increases so much that the application might arrive to be no longer memory bound, but compute bound. Moreover, there are limitations that are related to the bus and to the memory banks. So further study may help determine if it is feasible and even useful to maybe parallelize the computation so that the design becomes no longer compute bound.
So thank you, Paolo, for your presentation. So I'm stop sharing because now I leave the stage to Giuseppe, who is online, and will please share your screen.
Yeah, thank you, Davide. And hello, everybody. I'm Giuseppe Sorrentino, and today I will accompany you beyond the limits of FPGAs, proposing a versatile-based framework for bilinear interpolation. But before describing the project, let me introduce myself. I am a PhD student in information technology. I'm a first-year PhD student at Politecnico di Milano, and my main research interests are reconfigurable architectures, federated learning, and image analysis. And regarding all these interests, today I will present a project that starts from the image transformation and extends it to the interpolation. Considering image transformation, it consists of moving a pixel from one position to another. This movement has some approximation, which lead to some errors. And the idea of the interpolation is to mitigate this error, so obtain as output a smoother image. This has a lot of different applications, for example, in mobile and robotics for digital zooming, or also in the healthcare domain for image registration. And given its importance, state-of-the-art provides a plethora of different algorithms to perform this interpolation. But among them, one of the most employed is bilinear interpolation, which represents the best trade-off between accuracy and performance. It consists on computing the output of a single pixel by combining the value of 4 different transformed pixels. And also considering the formula, essentially it is a weighted sum, it has some critical challenges. Indeed, we have to perform 4 transformations, so we have to perform 4 times memory accesses than simple image transformation. We have to perform intensive floating point computations to compute the weight and then lead to approximations and so to errors. And also, since the interpolation must be overlapped to the transformation, we have to parallelize it as much as possible. And it has a very complex parallelization due to random access pattern and data dependencies. Given these challenges, state-of-the-art presents some solutions, some software-based solutions, like SimpleITK, MATLAB, Cornea, or OpenCV. All of them achieve very high accuracy, but at the cost of performance or energy efficiency. To target very high performance, some of these state-of-the-art libraries also presents a GPU-based solution that achieves very high performance and still and high accuracy at the cost of energy efficiency. Indeed, GPUs are too power hungry, and so they cannot be employed in power-constrained scenario. On the opposite side, we also find FPGA-based solutions, which are very performant and also very high energy efficient, but they do not scale. Indeed, these solutions can handle only very small images, and considering 3D images, only small volumes can be analyzed. Given these limitations, today I will merge the benefits of AI engine and FPGAs to exploit the versatile system and creating an heterogeneous solution, achieving higher performance as a GPUs and also high energy efficiency as a common FPGA. Considering versatile systems, no state-of-the-art solution exists for the image interpolation. However, for the transformation, we have the previous talk. And if you have not attended it online, you can find it online on the NECSTLab YouTube channel. We can use the image transformation presented by Paolo as an initial step for our interpolation. Considering the formula, indeed, we have to perform four times the image transformation, so we can replicate the presented design to parallelly perform these transformations. Then, given the formula itself, we have to compute the weights, and these are all floating point computations. For this reason, we rely on AI engines to perform this computation. Indeed, thanks to the AI engine API, we can compute up to 32 pixels per iteration. We can enhance performance, and we are less affected by the approximation of floating point computations. Furthermore, we tailor the procedure to perform this computation parallelly to the transformation step. According to the formula, we have to compute then the top and bottom factors, which are 2 independent factors. But as I said, we have to perform the interpolation in a streaming fashion, so within transformation. To do so, I devised 2 different coefficient interleaving and pixel interleaving mechanisms based on AI engine and MPL respectively, to give to coefficient and pixel a specific order. Let's zoom in the coefficient interleaving. We have 4 different AI engines computing 4 different coefficients. Thanks to the API, we can compute up to 32 coefficients per iteration. Then we can give this coefficient to the other 2 AI engines that exploit the intrinsics, very highly optimized functions of AI engine to perform the interleaving. The first interleaving step allows to alternate coefficient. Then these alternated coefficients are given as input to another AI engine that performs another interleaving step to organize pixels in a very specific order. Indeed, in this stream, every 4 coefficients correspond to the coefficient required to evaluate a single pixel. Obviously, this order is effective if also pixel fulfills it, consider it. So also on pixel interleaving, we have to organize the pixels. Indeed, we take 4 volumes transform, so the 4 transformation, we give this volume to 2 different processing elements, and then this on PL, and this PL kernel performs the interleaving. This interleaving allows to enhance performance since we are exploiting also the transformation, the Hebbe-Paulus for 3D image registration, and so we are inheriting its assumption. Indeed, we translate on X and Y, and we rotate around Z, targeting a very domain-specific transformation for 3D image registration. In this case, the coefficient computed for a single pixel can be applied to all pixels depthwise, enhancing performance. These streams, from coefficient and pixel, are then given as input to 2 different AI engine components that can exploit the AI engine API to compute top and bottom factors. Thanks to this, we overlap the interpolation step to the transformation step, strongly reducing the execution times. And now, once all the components have been computed, we can finally compute the intensity of each pixel, of each output pixel, by a weighted sum. The computation is performed on AI engine, and then the result is returned to a PL component that saves it on memory. Indeed, the AI engine itself cannot access memory directly, so we have to use PL for this task. Well, this design is effective, but it's not efficient. Indeed, we have a bottleneck. We are still compute bound, and so we had to analyze each kernel of this design, and we highlighted as the bottleneck last part of this computation. So we duplicated this design, obtaining a 2 times speed up, so improving performance. To analyze the design, I used as a dataset a volume of 246 slices with a resolution of 512 times 512. So higher resolution than state-of-the-art solution based on FPGAs. At the device, I target a Versa VCK 5000, and I compare myself against Cornea, accelerated on high-end GPUs, as the A5000 and the A100, and also MATLAB, accelerated on RTX 4050 Mobile. To evaluate this performance, I use as key performance indicators the execution time in terms of seconds, the energy efficiency employing state-of-the-art metric, and accuracy in terms of mean square error. For the first analysis, considering the execution time, here the lower is the better, we achieve top improvement against Cornea, accelerated on A100 of 2.77 times, and we are comparable to MATLAB, which is a very highly optimized cluster solution accelerated on GPU. But considering the energy efficiency, and here the higher is the better, we achieve top improvement of 9.2 times against Cornea, accelerated on A100, and we are also more efficient than MATLAB with an improvement of 1.4 times. Then we also evaluated the accuracy of the framework of the solution in terms of mean square error, comparing the presented solution against Cornea and MATLAB. And the solution achieves a lower mean square error against Cornea and MATLAB than the mean square error between them. So we improve the accuracy of our framework, and we prove that we can apply it for real application as MATLAB or Cornea. This concludes essentially the presentation. The design methodology allows to create a linear interpolation algorithm that solves some specific research challenges. Indeed, we balance the workload between programmable logic and AI engine. We parallelize the transformation and interpolation, solving the issues related to data access pattern and data dependencies. And so we achieve high performance, high accuracy, and also high energy efficiency, than state-of-the-art solution. However, the work is not finished. Indeed, we can parallelize it even more, pushing the limits of versatile system capabilities. We can also relax the domain-specific assumption, and I'd like to relax them to create a more general application. And finally, since we had to consider 4 times the memory accesses of transformation, but we are transforming 4 times the same volume, I also like to devise a caching mechanism to improve data locality. On this path, if you have some similar scenarios that can be parallelized thanks to the presented strategy, or other versatile devices that I can use to test my design, please drop me an email and I will be more than happy to work with you. Thank you for your attention.
Thank you, Giuseppe, for your presentation. So I have a question for you. You are talking about limits in of the proposed solution so far. So why are you talking about that? And do you have any plan to deal with them, or what else?
Okay, thank you for the question. Well, to improve the bottleneck, to solve the bottleneck, we duplicated the last part of the design. Now we are facing some limitation for the AI engine since we are exploiting all the streaming output of the AI engine itself. So we have to create a data duplication step to allow to use more AI engine and more interpolator components, and so improving the parallelization in the last step of the computation. So essentially, we have to create a data parallelization level, a data duplication level to improve the parallelism.
Thank you, Giuseppe. So this is basically concluding session of domain-specific computing. Please stay tuned because in 20 minutes from now, we will have the last but not least session. So I leave the stage to Marco.
Yep. Thank you, Davide. So as Davide was mentioning, what is going to happen now is that we are going to have a break till at the starting of the next session that is going to happen more or less in 20 minutes. So we hope to see you back at 8:25 Italian time, or otherwise according to your time zone. So thank you and see you in a while.